Hey guys, this is Mr. Oliver. This is going to be the solution for AP Physics 1, Unit 5, free response question number 2. Let's go ahead and get started. Okay, so once again, we've got another spinning disk rotating through its center. There's a student that's doing an experiment on the disk, and there is some friction between the axle and the disk. Okay, so that means that it's not friction free, and there's going to be some kind of a resistive torque to this disk. Now it says at question A, at time t equals 0, the disk has an initial counterclockwise positive angular velocity. So this, once again, this disk is rotating in the same direction that the ladybug problem just did. And so it's rotating in a counterclockwise direction with an initial speed of omega naught. The disk later comes to rest at time t equals t1. So a later time after it starts is going to eventually spin to a stop. And it tells us on the grid at the left below, sketch a graph that represents the disk angular velocity as a function of time at t equals 1 second. All right, so here's the thing. If you've got some kind of a disk and there's a constant torque, the word constant is actually pretty critical. That means that there's a constant force or a constant acceleration acting on the disk. And so that means that you would treat this problem as an old kinematic style problem, and the graphs would be corresponding to kinematics or constant acceleration type of situations. And so for this disk, if it starts at 0 time and it has an initial speed, initial counterclockwise positive angular velocity, it has to start here. And it says the disk later comes to rest, so the velocity at t1 is 0. So it has to have 0 velocity at that final time t1. Right? So what do you do now? Well, if you remember, for a constant acceleration, in this case it's a negative acceleration because it's slowing down, that's going to be a linear change in velocity, like so. All right? And if you need to remember why it's linear, look at the equation for omega. Omega is equal to omega naught plus alpha t. Okay, that is a linear equation. All right, and another thing to recognize is that this alpha, this angular acceleration term, would be the slope of that line right here. Okay. And so if this is a negative slope, then in the second question when it says to sketch the angular acceleration, well, I don't know exactly numerically what that is, but I do know that angular acceleration has to be constant, which means it's a horizontal line, and it has to be negative. And so that'd be representative of the acceleration. Okay, question B now says, the magnitude of the frictional torque exerted on the disk is tau naught. Derive an equation for the rotational inertia of the disk in terms of tau naught, omega naught, T1, and physical constants. All right, so this question is not super tough. You just got to know where to start. Anytime it ever says to derive anything, you need to think of top level equations, something that's a general thing that applies all the time. And so in this case, Newton's second law for rotation, torque is equal to I alpha, is a good place to start. All right, so we know what the torque is. It's a constant torque, tau naught. So I know what that is. That's tau naught. I is what I'm looking for. So we'll just leave that as I, but I don't know what alpha is. So alpha, because it is a constant acceleration, I'm going to use a kinematic equation. Omega is equal to omega naught plus alpha t. The final speed, because it comes to rest, is 0. So that means we have 0 is equal to omega naught plus alpha t. And so therefore, when I rearrange and solve for alpha, alpha is equal to minus omega naught times t. And in this case, the t is actually t1, is when it actually stops. So at t1, the speed is 0. right? So now I have an expression for alpha, which I'm going to substitute in my original equation right here, minus omega naught over T1. And then just take this equation, rearrange, and solve for alpha, for I. I is equal to negative, because there's that negative sign, tau naught divided by all this stuff. And so when you divide by, it kind of flips the terms around. So we'll have T1 on top and omega naught on the bottom. So that is an expression for the rotational inertia I. All right, question C says in another experiment, the disk again has an initial positive angular velocity, omega naught at time t equals 0, at time half of t1, so right here in the middle. The student starts dripping oil on the contact surface between the axle and the disc to reduce the friction. It doesn't say it takes the friction away completely, it just says reduce. As time passes, more and more oil reaches the contact surface, reducing the friction even further. So over time, that friction and thus the torque and deceleration kind of decrease. Never really reaches 0, it doesn't say that. It just decreases. And so then what we want to do is graph what the velocity looks like as a function of time, and then also corresponding acceleration. All right, so originally with no friction, or with friction, I'm sorry, we started here and we ended here, right? And so ideally what would happen is if there was friction, just like there was before, you'd have a straight line once again. But it says that halfway, and this what this little line is here, at halfway something happens and you start to add oil to it. So up until that time, it goes just like it was going before, right? But after that oil starts to drop, the friction gets less and less. And so that means that the rate at which this thing is slowing down gets less and less. And so what you have to conclude is like, well, it's never going to get to 0. It's got to get to something, some kind of a process that's not quite as frictional. So you can imagine that over time, the speed isn't going to decrease as much. Now you can't just all of a sudden arbitrarily change direction on this graph. You got to kind of continue on. And so we'll just kind of have this thing curve up ever so slightly, showing that there is a changing angular speed, or the angular speed isn't changing linearly like it was before. It doesn't tell us enough information to get this exact, but just know that it has to be curving, right? And it can't curve down because it's not going to stop faster. It's got to stop at a lower time. So maybe off the page somewhere over here it would stop. And so then for the acceleration, once again, you would start exactly as you did for the first half. But over time, that acceleration is going to get less and less and less. And so I don't know, it's probably never going to actually hit 0 acceleration, but it's going to get closer and closer to 0. Now, it doesn't exactly say it, but I'm just going to go back to kinematics, and anytime I see a curvy graph, the one below it is linear. So I'm just going to make a little some kind of a linear graph up to T1, like so. There's no real way to know, and in fact, on the rubric, it doesn't take off if you don't draw a linear line. Any kind of acceleration that changes its shape, getting closer to the axis. So it could have changed like this. It could have changed like that. It could have been a curvy line. You don't really know, as long as it gets closer to the axis. All right, question D. Looks kind of complicated, but it's really not. It says the student is trying to mathematically model the magnitude of the torque exerted by the axle when the oil is present after time 1/2 of T1. The student writes down the following two equations, each of which includes some kind of a constant C1 and C2 with appropriate units. And so you got this convoluted mess of an equation. You're saying, what the heck's going on? Well, what you need to think of is like as time progressed, the friction made the torque less, right? And so that's kind of what you need to think of. After 1/2 of T1, the friction was less. That's a fact. And then, because the friction was less, we know, therefore, torque was less. So what we need to do is we need to see these two equations and see that if time goes on, does the torque get less? Does tau decrease with time? Okay. So our first equation, equation number 1, says that the torque is equal to some C1, that's a constant, it's just a number, times T minus 1/2 T1. All right, so here's what we need to do is we need to kind of get rid of all the mess that doesn't really pertain to us. A constant, who cares? That doesn't pertain to anything. 1/2 of T1, well, T1 is a known value, so this is also a constant. And so the negative sign doesn't really pertain to anything. So all that we need to know is, like, look here, the time is directly related, and you'd write this as a proportion, is directly related to the torque. So as the time goes up, what has to happen to keep this proportionality right is that the torque has to go up. It's a one-to-one thing. It's an actually linear equation, y equals mx plus b. Okay, and we saw that the torque actually went down, so this can't be true. Let's just check number 2 to make sure they're not trying to trick us. The second one has some kind of a constant over time plus 1/2 T1. And in this case, constant we don't really care about, half of T1 that we don't really care about. And so what we have here is that time is related to, or I'm sorry, torque is related to the time, but it's inversely related. Torque is inversely related to the time. And so in this case, if this denominator goes up, in other words, as time progresses, you get further and further along in time, the torque has to go down. And so equation number 2 is the better model. Is it correct? Who knows? We just know it's better than this one, because as time goes up, the torque gets less. And so it says, briefly explain why the equation you selected is plausible. That's why. Is that by having time in the denominator, it shows this inverse relationship with the torque. And this one is a linear relationship, which means as time goes along, the torque goes up, which is not correct. All right, and that's the answer for that last question. If you do have any other questions or comments, please let me know, and I'll be glad to help you out. Thanks a lot, guys, and have a good day.